Hello, JFocus, and good morning. My name is Fabio. This is Tim, my colleague Tim. Tim is the GraalPy lead in our team. We are working in the GraalVM team at Oracle. And typically, you know GraalVM for its native image ahead of time compilation feature, but that's not what we're going to talk about today. Today, we're going to talk about how you can supercharge your Java applications with Python. Well, let's start with Java. Well, Java is a perfectly fine language. In fact, it has gotten better and better over the years and is still getting better. So we love it a lot and we use it a lot. So why in the world would you start writing Python code and JavaScript code and whatnot and mix it with Java? We're not trying to convince you to write Python and JavaScript. That's not what we're here for. But if you think about it this way, we all know Maven Central and maybe other Maven repositories where you can get the software that you can reuse in your applications. And the Java ecosystem is super rich, but we cannot deny there's other ecosystems too that provide really useful functionality and features. For example, the Python package index or the NPM registry. So what we're trying to do is we're trying to allow you to use and make use of other ecosystems in your Java applications. In fact, giving you even the possibility to not leave your Java IDE. So that may sound a bit crazy, and we're going to show you with a couple of demos what that looks like. We're not going to dive deep into machine learning frameworks with Python or something like this. We just want to give you an introduction how this is supposed to work and how you can make it work in your Java application. So this is where our languages come in. GraalPy for Python, GraalJS for JavaScript, GraalWebAssembly or GraalWasm for WebAssembly. All of them are open source. They're maintained by the GraalVM team. And they are self-contained. They have no external dependencies. In fact, they're just Maven dependencies, as you will see in just a bit. And they run on any OpenJDK 21+. Well, as the GraalVM team, of course, we recommend using GraalVM as your JDK, because that comes with a Graal compiler, and the Graal compiler can be used as a Python or JavaScript or WebAssembly JIT, and therefore it can speed up your the guest languages significantly. And because we work in the GraalVM team, all of our languages are compatible with native image, so you can compile them into a native application, for example, as part of a Spring or Micronaut application, and make use of them. So if you are an IntelliJ user, you may be using GraalJS already, because IntelliJ last year moved their HTTP client from off Nashorn, and to GraalJS. So they have this little tool that allows you to interact with REST APIs through JavaScript in the Java IDE, and for that, they're using GraalJS. And within Oracle, we use GraalJS also quite a bit. If you take a look at the database, for example, you can write JavaScript functions, and that's also powered by our engine. There's plenty of more users in the wild, but maybe you've already been using this, and then you're a direct GraalJS user. So how does this work? Well, I already mentioned our languages are just 2 Maven dependencies away, right? So you either add this to your Maven POM, or these 2 lines to a Gradle configuration, and then this polyglot package allows you to interact with our context API. You will see that in just a bit. And then with Python or JS or WASM, you can pick a language. In fact, if you really want to, you can also pick JavaScript and Python at the same time, right? So this is where I think we should start with a demo.
Yeah, and this is where things might go wrong. Or not, hopefully. We'll see. So, all right. So suppose you are interested in trying this out. You want to try Python in your Java application. What you should do is, first thing, just go to our website. It has documentation, compatibility lists, all that stuff, and most importantly, has a quick start. This gives you the snippets that you've just seen on the slides to put GraalPy into your Maven or Gradle project. These are the coordinates, so you can use them on other build systems too. And this is really all you need to evaluate Python code from your Java application. So if you just want to try it, you want to maybe add some scripting capabilities to your Java application, allow your users to script with Python, this is all you need. This is what you do. And the polyglot context API that you can see there, this is a sort of the embedded interpreter of Python inside the Java application, and it's very locked down by default, has lots of options. We have the Java doc for all the options that provides, and by default the Python code isn't allowed to access the file system, do I/O, start processes, start threads, none of that stuff. So it's pretty safe to try it out initially and then build from there. Fabio, however, promised to access the entire ecosystem of Python packages. And for that, we want to move on to the build plugins that we provide for Maven and Gradle that allow you to specify Python packages, and then these just get inserted during the build lifecycle into your Java application, and you don't need to worry about how does that even work, what is a Python package index. You don't need to know any of that. All you need to do is find a Python package that you want to use and put it in there. So one such Python package that I'm going to demo in a second is this little library that gives you QR codes. It has a nice friendly API. It just has a function to make a QR code, and then that object has a save function that allows you to save the QR code to a file or a byte stream. Now, what does that look like in Java? Well, it is very, very similar. So here's the Python code again that I just copied from the website, and I'm using this context API that you saw on our quick start example, and then it feels just like a Java object. You just call make, and you call save. Now this QR code class, that's not a class, that's an interface. And what GraalPy does for you is it magically makes it so that the Python objects backing this interface implement these methods and return other interfaces that implement even more methods. So that's all you need to add this package, and then, for example, if you're using the Gradle build plugin, you get this GraalPy section in your build, add a set of packages, you can specify versions. If you're, as Java users, you're used to having to specify all the versions. The Python ecosystem is a bit more lenient there. You can leave off the version. I would not recommend that. That does not lead to reproducible builds. So you can specify your versions here. And if you want to run this, let's go here. And I've set it up so that the console, that Gradle doesn't do this fancy progress bar. So you can see here, when I'm running this, it actually, as part of just the normal Gradle build cycle, after compiling Java, it has a task GraalPy resources, which pulls the package, bundles it up into the jar as resources, and makes it, and then there's this GraalPy VFS task, and that's what does the magic to make these Python files available to your Java application automatically. It's all bundled in one jar, and you can just use it like you would any other Java library and use the program against those interfaces. Now, this has been using this context API. We do have integrations into other frameworks as well. One such framework that we have an integration for is Micronaut. If you go to the, let's make this a bit bigger. If you go to the Micronaut launch website, you can add features to your Micronaut, your generated Micronaut application, and there is a GraalPy feature. So let's just add that. I'm just going to preview here what this does. And what this does is it adds two things. It automatically adds a dependency on the Micronaut Graal languages artifact. This is just a meta dependency that pulls in the languages that you want, in this case GraalPy. And it automatically adds a dependency on our Python, on our GraalPy plugin. So you can just add your packages right there. And I've already done this in a little example application. Pardon me. So here's a little demo to do just, it's a basic chat app, if you will. I can say, hello, JFocus. And there's some sentiment analysis here. Well, this is a pretty neutral statement. I've mistyped hello, so I'm guessing it doesn't really know that this is a positive thing. Good morning. Well, this is a positive statement. And the sentiment analysis here is just really very simple. But how is this done? It's, as you might expect for a Micronaut app, there's a controller, and it takes text that somebody has typed, and it analyzes the sentiment somehow. Let's make this a bit bigger here. And you can already tell, it's giving it away a little bit, that this method name is not camel case. So you might be able to tell, oh, this isn't just a normal Java method. And in fact, again, it's one of those interfaces that I've shown that maps directly to a Python package. So we don't do like magic method renaming. We just expose the Python interface as Java. So you do have autocompletion everything in your IDE, but it maps directly to what is documented in the Python documentation for a given package. And here you can see our nice Micronaut integration. And this is all you need to do to get this sentiment analysis package, Vader sentiment, into your Micronaut application. You don't need to write any Python code. The string Python doesn't appear in this application. It's literally just saying, I'm using this package. That's what I'm doing. And how was this interface arrived at? Well, you can just, you go to the Python docs, you see an example. Okay, there's this Vader sentiment package, and it has this sentiment intensity analyzer function that creates an analyzer, and that has the polarity scores function. And this is how you arrive at this interface. This interface I've written by hand. We do have in the pipeline a generator for these interfaces, similar to, you might have heard of JExtract for C++. We have a similar thing in the pipeline that would generate these interfaces from any Python package, and then you can just pull these in.
And you can see this is not just working for primitive data types. So the polarity score function actually returns a Java map, right? And with the return value, you actually control what the proxy is going to generate. And in this case, it's returning a Python dictionary, and it's exposing it as a Java map. But if you put list in here, I guess you would also get some sort of return value. Or if there's no conversion, then you, of course, get an error at runtime.
Yeah, the magic of this is that any Python object that could satisfy the map interface, or any interface that you provide, we automatically match that one. So Python dictionaries are naturally just Java maps. Python lists are naturally Java array lists, Java util lists. So all of this, the idea is that you don't, as a Java developer, you can pull in these Python packages, but you don't actually need to worry about where they came from, that they are in a different language. It's all transparent.
And even though we tell you that you can just work with Java interfaces, program against them, and declare your import statement in a nice way, of course, if you have Python developers in your company, you can evaluate Python files directly. You can embed Python with Java text blocks and all that craziness. IntelliJ, for example, provides you with language injections, so you get syntax highlighting and autocompletion within your Java file for Python. So that's all possible, but it's not necessary.
Now, this was, both of these demos were very small, very just really snippets of Python code that we used in Java. But if the future that we envision actually comes to pass, where you can just pull in packages from the NPM or the PyPI ecosystem into your Java applications, your applications will grow bigger, and if you do have any trouble integrating these, you might at some point want to debug this. So how do you debug this? Because as we all know, debugging is hard. And oh, and here's where there we go. Debugging is hard. So that makes us sad, but it doesn't have to be. For all Graal languages, we have this artifact DAP, which stands for Debug Adapter Protocol. All Graal languages can be debugged using the Debug Adapter Protocol. It's a generic wire protocol for debugging. It's supported by VS Code, Emacs, NetBeans, Fleet. I'm not sure, Eclipse also, yeah. I'm not sure if there's an IntelliJ. I mean, Fleet supports it, so I suppose IntelliJ supports it too. So let me demonstrate this. So I'm gonna attach to this Python, to the running Python code. And what you can see here is in the loaded scripts, it shows a GraalPy VFS path. This doesn't exist on my machine. It's a virtual path of the virtual Python files that have been integrated into the jar. And here we can find the Veda sentiment Python file that was pulled in. And since we are running this polarity scores method, I already put a breakpoint here. Let's try this again. Debugging is hard. All right, and we have a breakpoint. We hit a breakpoint. So the answer isn't coming back. It's waiting for me to debug this Python part of the program. And this is just a normal full features debugger. So I don't think debugging is hard. Debugging is great. I can change this here, and can look at the token list. It's now debugging is great. And if I continue, I will get the answer that, yeah, debugging isn't hard. Debugging is great. So the sentiment of debugging is great is, of course, is happy. It's a happy thought. We should always think more happy thoughts. So this concludes the demo part, and it didn't work out all that badly. Now, if you didn't have GraalPy, but you wanted to do something like this, how would you go about it? Well, the canonical way to do this is microservices. You have a Java application, and you have a Python application, and they talk to each other somehow, maybe via a REST API or something. And I mean, this has advantages. The processes are independent. You can hire a Python dev and a Java dev, and they don't ever need to talk to each other. They can just exchange notes on their JSON schema. Might be nice. And the other advantage could be that you are free to choose whichever version of Java or Python you want to use for each of these applications, because you can move them independently. However, these are now two different services. They're separate. You need to orchestrate them. They need to communicate. You need to lock that down. There may be some overhead in the communication. In this example with the Micronaut application, I've just been moving a little string from Python to Java, right? You might be moving way more data than that. And that data needs to be copied and synchronized between these processes. Or you set up some complicated shared memory scheme, which is very nice for your security lead, because they're going to be very nervous. So what we offer with GraalPy and GraalJS and GraalWasm instead is embedding these languages into your Java application. You could think of this as microservices, if you will. It's all in one process. So the deployment is just as simple as it is for any Java application. Of course, it works with native image, so you can have a single binary that you deploy. And calls between languages are just calls in the same runtime. They're very low overhead, and you can share the data directly. The main disadvantage here is that you are now locked at updating the language versions of both Java, Python, JavaScript, WASM at the same time, because they need to work together. Good news here is that we as the Graal team, we're keeping up to date with all the latest features of these languages. We're updating very quickly to the latest versions. So you do have the latest features available all the time.
Yeah, unlike Python, for example, JavaScript has a specification, and our GraalJS implementation is ECMAScript 2024 compatible, and this year it will be 2025 compatible.
Now, there are still impedance mismatches, if you will, between those languages. Python famously has a global interpreter lock. That means while it can have multiple threads, only one of those threads can execute at the same time, so you can't actually scale out to multiple CPUs. The simplest setup for embedding GraalPy in your Java application is to have a single GraalPy context, basically one interpreter. Now, this can be accessed from multiple Java threads, but since the GraalPy interpreter has to follow the Python specification, the way CPython works, we also have a global interpreter lock. And if you're accessing Python from different Java threads, you are effectively serializing your Java threads now. They all become eventually blocked on the global interpreter lock of Python. We have a solution for that, however. Because this is just a Java API, to create a Python context, you can just create multiple contexts, one per thread. And these have separate global interpreter locks. And now you can already scale out your Python applications across multiple cores, which is something you couldn't even easily do if you just put it in a single microservice, because then you actually would have to start multiple Python processes if you're doing a microservice architecture. This setup is slightly more complicated because you need to worry about setting up multiple contexts per thread, but you can get all the throughput that your CPUs afford you. And your favorite Python packages for machine learning, data science, they all should just work. And many of these just do. Yes, there's a question.
Question.
That is a very good question.
The question is, what about packages with native libraries? And in fact, most of the packages that we had on the slide here, they are using native extensions, right? So very good observation, and that's what we're going to cover in the next couple of slides. So
this is exactly, I mean, if you hadn't said that, that's perfect. Like, we didn't pay him. This was exactly the issue that everyone faces sooner or later. They realize, oh, I never used Python before, but there are all these machine learning libraries that are so hot and I want to use them. And then very quickly you realize that they aren't actually written in Python. Python is a thin layer around a huge chunk of C and C++ code in most of the cases. And yeah, how do you deal with that? You can't just, you can't just have a native library isolated 10 times in your process, or can you? Well, with GraalPy you can. Remember, we control the interpreter, and we intercept any time that actual Python code wants to access native libraries, and we transparently redirect that to different copies in memory of those native libraries, so that the operating system dynamic library loader will isolate these native symbol namespaces for us. This isn't process isolation, but this is library isolation. So these libraries now live multiple times in your process space, and they're independent. And you can actually scale even workloads that use native libraries across multiple cores in one process. And I've just run a simple pandas example where I'm analyzing, like, this was like a half gigabyte CSV files, and I just dumped like 20 of them on a Micronaut app to analyze them in parallel across different context pool sizes. And you can see it scales reasonably well on this machine. This machine has 6 performance cores, so that's why it kind of bottoms out when I go to 5 parallel threads here, because then, yeah, we're just saturating what this machine can do. But yeah, so the answer is, even for native libraries, you can scale with GraalPy across your available CPU cores. But there's more. There's another little tiny thing with native libraries. It's not just, native libraries aren't just functions. Native libraries also manage their own memory. And the JVM and Python, they want to manage memory for you. So if I was saying earlier that you can just share data between Java and Python. And that is true if everything stays in actual Python or Java code, because that's the managed heap. But if you're using a library like Pandas, the first thing that Pandas will do is, that's very kind of you to give me that managed data structure. I'm going to copy all of that into native memory right now. And Pandas isn't going about it very smartly. It does use Python APIs for this, so it still does use hold the global interpreter lock. And again, if we go back to my little example that I had with like 0.5 GB CSV files, you end up waiting for Pandas to copy, using only one core, your data into native memory, and then you're only doing a little bit of processing at the beginning and the end. And you're also using quite a bit of memory. Again, though, GraalPy has a solution for this. There are already interchange formats that allow you to exchange structured data in native memory between different libraries and runtimes, such as the Apache Arrow format, which has libraries available for Java and for Python and for Pandas. And we use that. If you put that in your application, we can use that transparently. And then this way, both your Java code, your Python code, and the native code that your Python libraries may be using are actually accessing the same data. And if you use the Java Arrow library, it is still managed, the lifetime of that memory is still managed by the JVM. And that same example, instead of using, I don't know, what is that, 12 minutes, runs in 30 seconds, because we're not waiting for a huge data copy. We're actually not copying any data. If you look at the blue graph here, that tells you how much memory we're using for this request, on the left-hand side, if you copy the data, you use twice as much memory. And this is the same problem you have if you have a microservice architecture. You now need to provision twice as much memory because you're gonna copy it. And we get around that with GraalPy. You're using half as much memory. So you're faster, use less memory. It should be a win-win. Now, again, what about your favorite Python packages? Well, most of them just work. Many of these already support the Arrow data format. We can isolate them across multiple cores. And you can actually, with GraalPy, scale up and scale out when you use these packages. Now, I said we support most of them. There are always little corners that might not work perfectly. We're always continuing to improve. We're working on this. And we have a compatibility page on our website where you can just put in what packages you're using, and it will tell you how many of their tests we're passing.
And if your package is not in that list, feel free to open a ticket so we can take a look and make sure it works.
Yes, that list of packages that is on our compatibility page has grown over the years. We keep adding things. And at this point, we're running the top 500 packages, a little more actually, nearly 600 now, every single day to make sure that we don't regress on their tests that we're already passing. One little thing about the native extensions still to mention, worth mentioning, is that the Python ecosystem, this isn't so common for Java folks because we don't deal with this as much, but in Python, since you have these native extensions, what the ecosystem has done is they created a way to ship ready-made binaries for different platforms. So when you install, you get a binary and you don't need to build that native stuff from source. However, these binaries are tied to the specific version of Python that you're using. And unfortunately, not all of those top 500 packages are shipping binaries for GraalPy just yet. We are working with the upstream developers to do this. In the meantime, we are publishing our own builds in GraalVM or Python wheels.
So before we dig into the next demo, I'd like to summarize this real quick. So for you as a Java developer, we're trying to integrate Python as nicely as possible. You can depend on Python packages in your Maven or Gradle configuration, right? You can program against Python interfaces. That's what you typically do with libraries anyway. You think about APIs. You don't really care how it's implemented, right? So you program against an interface, and with our native integration that we've just talked about, we also bring Python closer to the Java model where everything is really easy in terms of concurrency. You can just spawn threads and run them, and we can even do things that the normal Python interpreter cannot do, like running multiple native extensions at the same time in the same process. So those are the things that we currently work on, and keep us posted how you want to use Python in your application, and we try to make that work too. So if you've read our abstract, we also mentioned that we want to show a JavaScript and a WebAssembly demo. Oh, that's what we're going to do now. So there is this cool project online, which is called Photon. It's written in Rust, and it's an image processing library that can be compiled to WebAssembly, and then it runs in the browser. And maybe, Tim, you want to take it from here?
Sure. Yeah. So this is, this is the demo website for the Photon library. They just have some default image, and you can click on different filters. You can flip the image vertically, horizontally. It tells you how much time it took to run. I don't know. Maybe there's a Rio. That's a fun, funky effect. Now, again. Yeah, this is one of those cases. Oh, this seems like a neat library that you might want to use, and there might not be a ready Java implementation just yet. So, what's the issue? Well, this is WebAssembly, and there's a JavaScript wrapper around it. So we have just taken this and put it into a Java app. What does that Java app look like? Well, it's this. I was demonstrating Micronaut first, just to show you that we integrate with other frameworks too. This is a Spring app, so here's a Spring service, and I mean it's just as simple as you would expect. There's a process function that the service takes an effect name, and then it takes this Photon interface once again and makes a new image with that effect. Now, what do you imagine that Photon thing to look like? Well, again, the Photon image is an interface, and here we are using a slightly different API because WebAssembly, if you've looked into it, it doesn't give you an object-oriented nice API that you can just map to an interface very easily. So there's a tiny bit more work involved. You have to use these functions to get members, invoke members. But other than that, it doesn't really look like you need to have a huge JavaScript or WASM knowledge. You could just still get bytes for this image, and then return this as a Java byte array.
And I should mention that in this demo, and if you're using, for example, if you're compiling with Rust to WebAssembly, then you get a WebAssembly file, but these compilers also provide you with JavaScript wrappers. Tim briefly touched on this, and this is how you can exchange complex data types. And typically, when you directly talk from Java to WebAssembly, you now need to know a lot about the WASM side. Like, you need to know how are strings laid out in that language, the language from where the WASM was compiled. And this is all very complicated. The WebAssembly community is working on this to make interoperability better. But the best that they have right now are these JavaScript wrappers that are automatically generated. And because we have a JavaScript runtime, you can use them too. So in this demo, we're actually not calling from Java to WebAssembly directly. We're calling from Java to JavaScript wrapper to WebAssembly. And while that sounds crazy and sounds like a lot of overhead, it really isn't.
Yeah. Let's maybe do a hey for 10 seconds. So here's I wanted to show this. So here you can see this is the WebAssembly code that is measuring just how long just running the WebAssembly function to do the image filter takes. Here it says time 15 milliseconds. But this is really measuring just inside your browser how long the WebAssembly function takes. It doesn't measure the whole round trip through the web server. With Hey, we can kind of approximate that. We're going to measure the entire round trip through Spring, through netty, and through the WebAssembly interpreter. I'm going to let this run for 10 seconds, and then we can see, oh, okay, we get about 130 requests per second, and this is about, what is this? Like 60 milliseconds from not very warm, just started, for the whole round trip, for something that, you know, where just the WebAssembly code itself takes about half of that time, and the rest is just in the web server.
Is this running on hotspot or on native?
This is running on hotspot.
Okay, yeah. Well, you can also compile the app to native and run it the same way. In fact, you'll find the demos in our demo repository. We'll put up a link in just a second.
Yeah, this is, let's go back here.
Yeah, but to summarize, we want to allow you to take advantage of other language ecosystems, for example, Python, JavaScript, languages compiled to WebAssembly. And for that, you can use GraalPy, GraalJS, GraalWasm, and other languages that we provide. Since last year, all of the 3 languages are considered stable and ready for production. JavaScript has been for quite some time, but Python and WebAssembly, we added those last year. They're self-contained. They run on OpenJDK 21+. They run best on GraalVM. They're integrated in Micronaut already. There's also a JavaScript integration that allows you to do server-side rendering of React components in Micronaut. So you can render JavaScript React components as part of your Micronaut application. And we're working with Spring and Quarkus to integrate our languages as well. And in the DevOps talk that Thomas and I did last year, we were very excited that Python is now stable and WebAssembly is stable too. We've received a lot of feedback. People like the gentleman in the back, they were like, "Oh, I want native extensions, and I want to run them in parallel in all of my Java threads." Right. So the 2 new features that Tim described, sharing data using Java Apache Arrow, and the multi-context support are all new features that are coming up in the next release, and hopefully that demonstrates that we're listening to you. So provide us with feedback, test out these things, let us know how you want to use them, and we'll try and make them work. So if you want to try it for yourself, here's the QR code. On GitHub, you find a Graal languages demo repository with a bunch of demos. The Photon demo is in there. A debugging demo is in there. The guide with a QR code is in there. There's a JBang demo. There's a Micronaut demo. There's a Spring demo. Take a look, try them out, and let us know how you go. And with that, I think we're ready to take some questions.
Yeah, just to demonstrate, we have a JBang integration, and that QR code was actually also generated with Java code calling the Python QR code library through JBang. So that's all in there. Self-contained, meta-circular.
Yeah, well, thank you very much for your attention, and now we're happy to take any questions.
We have some license checkers in our build steps in the pom.xml. Like when we integrate this the Python libraries or JavaScript libraries, and they have some licenses which are like different. Will they be like automatically taken care of, or we have to do something like extra for those licenses, like open source licenses?
They're not currently automatically taken care of, but it is actually on our roadmap already to extract those licenses too for the Python and NPM packages and make them available in the life cycle so that later they would be just like any other dependency and that any other plugins could just pick them up and wouldn't even know that it's Python dependencies.
Okay.
It's a good question, thank you.
Yeah, thank you.
Yeah, there's a question back there.
Do you already have any plans for the next community you want to support? The next language? Like, is something already in the making there, or you guys are thinking about it?
We are listening to, I was going to say who shouts the loudest, but we are listening to what the community actually wants. I mean, if you look at the history of the GraalVM languages, we have other experiments with other languages, and we've done other experiments for other languages. It's in the past few years, JavaScript, WASM, and Python were just the most prominent candidates where people were asking, where the most people were asking, and that seemed to have the broadest appeal. So I wouldn't say we have concrete plans at this point, other than we're still open.
I remember there was this LLVM experiment somewhere.
Yes, that exists. Not much to say about that experiment.
It's
Yeah.
still around. You
Okay.
can still use this, but in some regard, LLM as an
LLVM.
intermediate language is just like WebAssembly, and
Yeah,
it
yeah.
seems like WebAssembly has a bit more uptake at the moment.
Mm.
In this regard, in fact, like Python and other runtimes, like JavaScript, they're integrating WebAssembly now, right? So that's why we're targeting WebAssembly. There's a bunch of other languages, also research languages that you can play with. But yeah, the developer community, they're really focused on Python for machine learning, data science. JavaScript dominates the web. TypeScript is something that we have played around with. We could make that work in the runtime if we really need to. But then again, you can compile it to JavaScript and run it on GraalJS, right? So yeah, right now I don't think we have any concrete plans to expand that list. But maybe plans change.
I was curious about, assume that you want to build a web application in Java, and that you would like to avoid using JavaScript in the front end, actually running in the browser. I was curious about if you could comment on the possibilities of, or potential or not potential of writing an application in Java, running on the back end, and having the web GUI running in the browser based on WebAssembly.
Yeah, so JavaScript started out in the browser, and then the JavaScript community were like, oh, we can do front end, but we want to do back end too. And then they decided to use JavaScript on the back end as well, right? So there's a lot of server-side rendering going on in Node, right? Like with React, for example, you can do these things too. And then you don't
Just to double check, your question was about backend computation, or was your question about moving more of the Java stuff to the front end?
No, the other way. I was more after moving away from using JavaScript in the browser.
I see. Okay.
So I was thinking about if you had any ideas
Well, there
or
is
plans or you know, ideas on. Yeah, exactly. So I move it to the back end.
There
similar
is
to
something.
so do something with WebAssembly similar to what HTMX is doing, you know.
So what we, so our WASM runtime doesn't run in the browser. We do have a node built on top of our GraalJS, but and yeah, we said well, native image is still a very big part of, or the most popular part of GraalVM. So on the native image side of things, we are working on a WebAssembly backend so that you can compile your Java application to WebAssembly.
And then run that in a browser.
If you're curious and want to learn more, I'm actually going to demo this at WASM.io. So then you can run Java C on the mobile device, for example.
Yeah, we have JShell in the browser. It's completely running.
Control the different GUI controllers in the browser then, or.
But that's the next thing, right? That you can interact from. Well, you need to interact from WASM with the DOM, and I think right now you need to do this via JavaScript.
Yeah.
But we get there. I'm sure people will work that out.
Interesting. Okay.
Java.
Exactly. Thank you.